This is the last piece of formal lecturing in regard to the CO2 measurements and thinking about CO2 measurements. It's probably the least well-formed and adequately discussed, so this is really in part to provoke discussion in many ways, though I think there's a sensible scientific underpinning to some of the ideas I'm trying to hint at here. The problem is this, that anything you measure, you probably have an associated error with it. That error might be large, it might be small. Ideally, what you have, as we discussed in the quality control, is some statistical understanding of the range within that where error is going to lie. And we refer to that as the uncertainty. And one thing I'd like to point out to you is that the uncertainty is not the precision. We can't say that often enough, and probably it'll sound like we did. The uncertainty is not the precision. The precision of these methods in capable hands with experience on a good day when the laboratory gods are smiling on you can be really, really good. That's not necessarily the uncertainty, because ultimately you want to compare measurements one with another. Very rarely do you want to compare your measurement with itself. And so the overall uncertainty is what you care about. And then you have to remember that all the other things you're using, how much boron there is in seawater, what is the solubility of CO2, what are the dissociation constants? These also were measurements. These also have uncertainties associated with them. Thus, if you use them in a calculation, the overall uncertainty is bound to get bigger. A little bigger, a lot bigger. Do you know? How could you know? What would you do? That's partly what I'm going to talk about here. So, to return to this picture, the idea was we had 7 species, 4 equilibrium constants, 1 total thing, need 2 more. That's the tradition we've talked about. And much of the discussion is there a magic 2 that's better than any other? And the answer is sometimes. The 4 possibilities we've talked about. So this is really the key. Mathematically, the equations that are implemented in programs like CO2sys, CCarb, CSys, and a few others, mine is called CO2 Calc. You can run one measurement set of data at a time, but you can look at it pretty carefully. Yeah, they can do the arithmetic. And with care, the arithmetic is correct. But every one of these terms has an associated uncertainty. These uncertainties propagate through the calculations, ending up in having an uncertainty. And the uncertainties, as I said, are in the measured CO2 parameters, and they're also in the constants. And I'm just going to give you one little piece that, to me, is a flavor of this, because it shows that not only do we have uncertainties, we're uncertain as to what they are. Even uncertainties have uncertainties upon them, right? You say the standard deviation is 2, it's not. It's a range around that you believe is around 2. 2 is your chosen point in that range, but it's not perfectly 2. So here's a set of data from a couple of very careful laboratory studies by 2 PhD students on either coast of the US. One at Scripps, Tim Luca. This is from the Luca et al. Paper published in 2000. One in Miami, Kitek Lee. And the data here have been represented. They measured seawater samples with different FCO2s, and they have calculated from measurements of alkalinity and total carbon, done as carefully as they knew how, the FCO2 and compared it with a measured value. And the scale here shows the percentage deviation from that measured value. This really is as good as it can get. One, Luca is using the same methods we use to certify the reference materials. And so they've been fairly carefully studied. Kitak had a lot of experience and was using the reference materials to make sure that his methods were working well. So there's not total independence between those two laboratories in that thing, but there's a lot because it's different equipment, different people. And you see, this is really reassuring that you can indeed calculate the fugacity of CO2 from alkalinity and total carbon and get the same numbers if you measured it, provided you were less than a number of 500. Here's the rest of the data set. I have no idea why it looks like this. So there's an uncertainty there that we're still uncertain about. My discussion going forward doesn't account for all of these. It's just as we start to learn that we recognize that, is this because we can measure things okay in this region, but by here we can't measure them as well? Perhaps. Is there something odd about the chemistry that we ought to do? You could get all these points to come to this line by assuming that K2 varied with the amount of CO2 in the solution. An inconstant constant. Would you expect it to do that? Not really. Should you therefore use that K2? In my opinion, probably not. But we don't know. So it's not as tight as you'd hope. But the basic approach of asking how should we draw these error bars to see whether or not they actually are crossing that line is a propagation of uncertainties problem. For any measurement, y, it's usually a function of a whole bunch of things that go into it. In this case, carbonate ion concentration is a function, even in a very simple system of a seawater, of those 7 things that went into that. The uncertainty on it is therefore depends and that those 7 things were independently measured. This formula assumes they're independently measured. There's not a correlated error. And with care, that's relatively straightforward to achieve. If you use the closed cell titration to get your total carbon and your alkalinity, those errors will be correlated. And that would have consequences, and you'd have more terms out here accounting for that in a formal thing. Typically, we assume that's not the case. So what do we need to know? We need to know what the uncertainty is in every one of these parameters. And that takes time and trouble to get. And we also need to know how the sensitivity is. How much does y change for a change in x? That's very easy to conceive of, but if you looked at the formulae for calculating these things, which include such things as solve this quartic equation for hydrogen ion concentration, it's not, typically we don't have analytical solutions for this. They're usually obtained numerically. You say, here's my answer. I'll perturb one of the numbers a little bit and therefore calculate what happens here. I did this in my youth. This was the first paper I published from my PhD. You'd think somebody could get a life in the meantime, wouldn't you? And here we did it a little differently, but this is the only one you can go to the literature and actually look up some of these sensitivity parameters. We said that we're going to do it in terms of relative uncertainties. That is, not how much does carbonate ion concentration if I change alkalinity by 1 micromole per kilogram, But what percent will carbonate change if I change alkalinity by 0.1%? And in actual fact, they vary a little less over space, because those parameters, this basically rearranges the equation in that way, that you get the relative uncertainty, and therefore we get this curious looking term, but essentially saying, if I had a 1% change in alkalinity, what would be the change, the percentage change in the other parameter? Here again, relative uncertainties. So in this paper, there are tables like this. This is one subset of a larger table where these uncertainty sensitivities, the sensitivities, were calculated numerically for a surface seawater sample. So this is appropriate for surface seawater. That's a limited number of the experiments you're actually going to do, but the idea here says that if we measure parameters with pH and total carbon, then if we're predicting the carbonate ion concentration, for a 1% change in hydrogen ion concentration, carbonate will go down. 1% up in hydrogen carbonate goes down by 0.88%. Almost 1 for 1, but not quite. A 1% change in total carbon, carbonate changes by 1%. K1, carbonate really doesn't matter. K2, it does. K0, if you're calculating PCO2, 1% this, a little more sensitive to hydrogen, sensitive to the K0. A little bit to K1, much less to K2. So we then, this latter column, which I'm going to come back to because you can permute this, if you take uncertainties just for the experimental data, the pH and the alkalinity, and total carbon, you can do this. But if you include uncertainties due to the constants, you get this. But probably, if you were to measure pH and total carbon with methods that had the uncertainties that I quoted in 1978, which frankly would be what I would call good methods today, because the uncertainties were underestimated. These are what you get. So if you wanted carbonate, you get about a bit less than 5% error in carbonate from what were then the best available pH and total carbon. Now, what are these uncertainties? Now, here is where I can annoy people, perhaps. These are my estimates of the uncertainties for the various methods. I would say that in state-of-the-art laboratory, really straining with reference methods like we do, where each analysis can take some of the analyses can take hours. An awful lot of work's gone into background calibration, things like that. This is what you could achieve. We think our uncertainty on alkalinity measurement is 1.2. Now, he said, just me. He said 1 for certifying that stuff. Yes, but I give you the average of a whole bunch of them. But I also add in another error for the stability. Total carbon, about 1. pH, 0.0003. PCO2, about 1. The problem here is getting that equilibration perfect. Now, any of these, on a good day, you're going to see better repeatabilities. For pH, strikingly so with the well-working spectrophotometric method. But this is accuracy and reproducibility kind of pushed together into a single number. That's the best you could hope for. State of the art. This is what the best labs get more routinely. Somewhat worse. Other techniques, if they use reference materials, probably fall in these ranges. If you don't use a reference material, have no idea. Have no idea whatsoever. You may have done a lot of work in your own laboratory to get that number, and if you do, you could possibly say, yes, but it overlaps with one of these. The question mark doesn't mean it's necessarily bigger than this. More likely to be, but necessarily, I don't know. So this is the key. And if you take that, and what I'm going to show you now is how much error this contributes to calculated parameters for all the different method combinations. And I'll caution you about this figure. First, clearly, it has too many significant figures. No question about it. But that said, this allows you to look at relative differences between them and see what I've done. So what have I done here? I've done the relative uncertainty in either calculating the unionized CO2, which is going to be related to PCO2 if we permuted, in addition, the error on the equilibrium constant, or on carbonate ion. On the basis, in my mind, that most of the discussions I've seen related to ocean acidification phenomena were discussing either what PCO2 was or the saturation state or something to do with the carbonate ion concentration. That's why I chose these two for this picture. Of course, you could do this for anything you wanted. It just takes time and trouble. So with the very best methods, you could, at best, get actually pretty good data. I think this must be a typo, but I'd have to go back and check. It looks too good. I think it might not be, because most of the uncertainties half cancel out in this style of doing it. And these are very small uncertainties. But you see that it's there. More likely you're over here. And this is really what I would say most people are going to be in this range. It takes a lot of work to get to here, and a lot more to get to here. Now, you're only 4 times better, but loosely that would mean 16 times the work, 4 squared. So, can you make choices between the methods? Well, clearly, it would be ill-advised to try and get carbonate ion out of pH and PCO2 measurements. That sensitivity stands out as a problem. The others, a little less so. This one is pretty good for alkalinity and total carbon. These ones for PCO2, obviously if you measure PCO2, which you did in all these, you're in that range. So saying there's a necessarily wonderful pair of parameters, that isn't quite there either from this way of looking at it. But you've got to be sure that you actually know what your uncertainty is, the discussion I had before. Because if you know that, you can calculate what the uncertainty is going to be in what you really want to know. And if you know that, you can say, is this good enough, fit for purpose, or not? If not, the easiest fix is a different method. The next easiest fix is to work harder. Really easy fix is, yes, well, if I have an uncertainty of 10 and I'd like an uncertainty of 1, all I have to do is measure this sample 100 times and calculate the average. But that's a lot more work. So there are trade-offs, but what I want to impel is it's you that should be making these trade-offs. Not saying you heard that total carbon and pH was the right way to go, therefore you'll do it that way. You should think about it. What do we need? This has not been as rigorously thought through in anything I've seen published. And so we're still there. We still need to. Why has it not been rigorously thought through? Well, there's a need for, number one, a community discussion of what are appropriate target uncertainties. What is it that influences your decision about target uncertainties? The people in the ocean CO2 fraternity have done this, but their push was to see anthropogenic CO2 changing in the surface ocean. And we thought about the numbers in that point of view and came up with guesses that we thought were at once helpful scientifically and achievable technically. For this, I've not really seen clear statements of what target uncertainties would be for these purposes. I'm sure you have them. Jean-Pierre is always saying, well, you know, for our kind of experiments, we don't need it that good. Presumably, therefore, there's a picture of how good you do need it. We need to get this discussion, and we need to have it and make it clearer in a broad community. We actually do need to know how well we're actually making the measurements. All the numbers I gave there, I say would be contentious. If you were one of the labs relying on your data being great to keep getting funded, the larger uncertainty I probably allocated than you thought you had would be off-putting to you. You may be better if you've got the system in place to think about uncertainty and calculate it. If you don't, you're just asserting it based on this afternoon we got some good results. That's not entirely convincing. So there's a need for a more rigorous evaluation of the various methods. The problem you've got is we haven't done this, and you want to buy it the next time somebody gives you a checkbook. And so there's a little bit of catch-up to be done here to do it well. And this would be a lot more straightforward if you could also type in the uncertainty into this program and get the uncertainties on the calculated values coming out. There's a hint of that in version 1 of CO2sys, where the sensitivity parameters are calculated by Ernie Lewis. But of course, you have to say what your uncertainty is, and mine, doing total carbon by acid extraction with a vacuum extraction and a manometric determination, is bound to be different from somebody who's just squirting some acid in and then having the CO2 diffuse across a membrane and measure the change in conductance in the fluid on the other side of that membrane, which is a method people have used for pore waters, for instance. So if those three are there, it's going to be simpler to do this, to judge fitness for purpose and to optimize the resources needed to do the CO2 measurements. You will always get better measurements if you spend more money wisely. It's not just spending your money more. The care that you put into it should be appropriate to what you need. So thinking about what you need should be step one. Here's a paragraph from this article I wrote for the Epica guide. I think you would agree with my first sentence there. If not, you either have far more confidence than I think you should, or you haven't been listening. Probably at this time, your fastest way to success is to link up with somebody that you can work with that can either help you set up the lab or actually just run your samples for you. To go into this completely not knowing, not ever having done it, buy the equipment, figure out how to use it, reassure yourself you're using it properly, all the rest of it is a big undertaking, and we don't yet have an adequate community structure to support you in this. As a group that we hope hope perhaps is not the right word. We believe this is a problem that is going to go for a number of years. It will need people working on a lot of different facets of this. It will need reliable CO2 measurements as a small part of that. It's dominated these 3 days, but this is a 2-week course. And of course, it could have been a 2-year course. So ask yourself, what am I gaining by just buying the cheapest equipment I can afford, the equipment I can afford, handing it over to my student and saying, I'd like some CO2 measurements come Monday? Is this going to work for you? It may, but think it through. There's a variety of ways of skinning this cat. You need a clearer understanding of the costs and the benefits. And you should be thinking about this right across the range, from the equipment, the people's time, the result you need for your measurement, the fact that if you send it to Dickson's lab, you might get the result back in 3 weeks, but it could be 3 months. But I'd rather like to have it tomorrow afternoon. If you need those results right now, you're stuck. You have to get this set up. So you've got to worry about that. In fact, you know, my first picture applies. So Chris is going to add his take on this and then enhance our discussion.